Hi everyone. Today I'm talking to Julian Leonard about fractional quantum Hall states. This is a very interesting part of quantum mechanics that I'll let Julian introduce himself. We're going to be quite technical in this discussion, just so that you're aware, and without further ado, I think we can jump into it. Julian, thanks a lot for joining today.
Yeah, thank you for having me.
We're going to be talking about the paper called Realization of Fractional Quantum Hall State with Ultracold Atoms. Would you mind, as an introduction to that, describing the research field that you're coming from and what led to the publication of this paper?
Yeah, sure. So the overall research field is ultracold atoms. So we work with atoms that you can cool optically to very low temperatures, and then you can do actually different kind of physics with it. And the kind of physics that I am usually doing with this is called quantum simulations, and that's kind of a subfield of quantum computing, or at least related to it. So that's, I would say, my general research background. And now this particular experiment was kind of the main project of my postdoctoral work. So I actually thought about it even before going to Harvard. So I was working in Zurich at the time, of doing such a project, and I discussed with my advisor at Harvard whether we could do something like that, and he was actually already for years very excited to do something along those lines, and so we wrote, or I wrote a proposal in Zurich with his with him hosting this project then at Harvard, and we went there, and we got actually first to do many other exciting experiments, but it was always kind of one of the focus of my postdoctoral work there, and then eventually it actually turned out to work, and no, it was great that it worked out. We were very happy.
Okay, great.
Yeah.
So would you mind introducing what FQH is all about, just on a high level to set the stage sort of for what we will be talking about?
Yeah, so it's to me it's one of the most fascinating things that you can have, because when you have many particles, then sometimes very counterintuitive things can happen. And I think FQH, the fractional quantum Hall effect, is really one of the most famous. Many particles can suddenly behave in a way that would just impossible for single particles. And in this case, the key signature is that these many particles together suddenly behave as if they had a fractional charge. So we know that charge is always coming in units of one of the elementary charge. So all particles, as we know, have elementary charges of say 1 or -1 or 0, and that is essentially just the electrons, for example, have -1 charge, right, and protons have charge 1. And you can also have more complex particles that are composite particles that are built out of those, and they may have higher charges of higher integers or of negative integers. But you never have a fractional charge. So at least not for free particles. Quarks can have, that's a specific maybe a specific example, but no actual free particle can have a fractional charge. And here we have something that actually does exactly that. So you put a bunch of electrons in a box, circumstances, they behave as if they had a fractional charge of 1/3, of 1/2, of, there are many different fractions in ways they can behave. So that's very, very surprising and very exciting as a physicist to see something like that.
Mm-hmm. Yes, and I think we'll talk about some applications of this in just a second, or potential applications. But first, I would like to just dive a little bit deeper in how this actually works. So I think we have this figure 1a here that kind of describes what the state preparation is for such a system. Would you mind describing just what happens, let's say, in this normal situation and then compared to when you have this FQH state?
Yeah, sure. So in what refers to as normal here is a two-dimensional gas of particles. And in solids, we usually have electrons that you can put in a semiconductor such that they really behave only in 2 dimensions. And behave in 2 dimensions means that it's so tight that moving the 3rd dimension would cost so much more energy than the particles have, that so you're at low enough temperature such that the 3rd dimension is just you can't access it as an electron. Here we're working with bosons in an artificial system, essentially, that mimics the behavior of a real 2-dimensional heterostructure, a semiconductor heterostructure. And in a normal situation, for example, when there's no magnetic field happening, these electrons, they would just move more or less freely. I mean, they're still cold, but they're still moving somewhat around. And now what happens under certain circumstances, in particular in the presence of a strong magnetic field, is that these particles, these electrons, they can now behave in a way that would actually only be possible to explain if they had a fractional charge. So the transport characteristics, for example, and also many other microscopic signatures, they change, and that is what we call here the fractional quantum Hall state in the right panel. Yeah.
Mm-hmm. Would you mind describing what the vortex is that we're seeing on here? So you have this kind of vortex behavior, and
very simplified picture. Mm-hmm. Sorry?
Yeah, please go ahead.
Yeah, it's a very simplified picture of what the fractional quantum Hall effect is, but I think it's really at the essence of the state, and that's why we highlighted this here. So a big class of fractional quantum Hall states, and they're called Laughlin states, they can be described by this kind of vortex motion, and what it means is that you have in solid would be electrons. Here we have these atoms that are behaving as if they were electrons, and these the way they behave now is that they essentially encircle each other. So you can think of each atom now, or each electron in a solid, to be in a state that means that it encircles all other particles simultaneously. Mm-hmm. And that's a bit, you have to wrap your head around this, because it's not really something that makes sense at first sight. So it's, one particle can go around another one, and it can also go around all the others, but that would mean otherwise it doesn't make sense. But here, it's a quantum mechanical state where these particles are distributed, and each particle encircles its neighbor, but it also simultaneously encircles all the others, and it's in superposition of entangling all of those. So it's a very particular state that has this wave function that really just describes this vortex motion. And so that's why this vortex motion of these particles is at the core of the fractional quantum Hall effect.
Do you have some conceptual understanding for how that constellation might, what that constellation might actually look like? When I hear you say that you have these atoms and that they're simultaneously in a system with more than two atoms, let's say, all circling each other at the same time, to me that sounds like an over-constrained system. Yeah. I don't know if there are particular constellations that are like easily representable that arise when you have this kind of behavior, or do you have some intuition for how, like, what that kind of constellation would be if you have these atoms that are simultaneously circling each other at the same time? Because I take it that they're not just going in some form of orbit, but that they're actually going in a more or less circular orbit around each other. Or is that is that assumption not correct?
It would be. I think I know where you're coming from. It would be over-constrained if you think of it in a classical world. But since these particles, they're kind of at the same time at every place, this constraint actually is gone again. So it's. I think like for constraints, we usually think of, like, I don't know, something is fixed somewhere, or you kind of fix the distances between particles, or these kind of things, right? And these constraints, they would occur, but that would also really mean that these particles, they're kind of bound to where they are. Here, no particle is bound to another one. They're still going. They can still go everywhere. It's really this this superposition of this motion. So a particle is not localized necessarily at one position. It can be somewhat localized, but it's not necessarily bound to its neighbor, because since it's entire, it's really not over-constrained.
Mm-hmm. What does it mean for, actually, maybe this is a naive question, but what does it mean for the wave function in this case, that for them to be in a vortex, let's say, you don't have a particle that's constrained to one point. What does it actually mean to say that these are circumventing each other if we're talking about distributed locations of these particles?
Yeah, so imagine, like, you put yourself in the position of a particle, any of those. So let's say we now move together with one particle, and we're always sitting at a position where any one of those particles sits. And what we would see is that all the other particles, they're going around us in a circle. And you can do this with any particle. You always see that they go like in a circle around you. Now, of course, it's a classical picture now, right? I mean, in truth, that these are wave functions, these are distributions. It's not only one coordinate, but simplified. I think that's what how you can imagine what happens here. So it's the relative motion of these particles that's what's so interesting. So the center of mass between pairs of particles, that these are always shown by these vortex motions. You can almost think of it as like a double star system, right? A binary star system, where also these two, they're orbiting one another, and that's kind of also how this wave function looks like here, except that there's a number of stars, and you can think of each of those being delocalized, being simultaneously in many different positions, and then encircling all the others.
Mm-hmm.
Yeah.
Okay. if we talk about sort of the practical aspects of this, or why we have an interest in these kind of states to begin with, beyond just the pure academical research, let's say, of how these systems interact, what would you say are the main kind of incentives for studying these kinds of systems?
I think that has actually changed a lot over the years. So when it started, this was actually born out of the integer Hall effect, where particles in like integer numbers. So essentially, your conductivity was constrained to integer values, and this turned out to be an extremely precise way of measuring fundamental constants. And so at the beginning, it was kind of a precision sensor. And the beautiful thing about this, maybe we can talk later about what topology means, but the beautiful thing about the state is that it's robust, and this is what we call, it's a consequence of what we call topological. Robust really means you can deform the sample, you can change whatever you want. Some constants stay the same, and that's unusual. Usually when you make a table 5% smaller, the mass decreases by 5%. Or things kind of change when you change things a little bit. But here, you change something by 10% and it does not change up to the last digit that we can measure. So there are some properties that seem to be unaffected by what we would do to the system. And I think that's what was the original interest in this fractional quantum Hall state, because it started as an integer, then people found these also fractional particles. It started to be a more fundamental question as well, on top of this high precision thing. And then later, people figured out that there are actually these excitations. So if you don't look at this ground state of these particles moving around one another, but actually you look at the first excited state. So how can I, when I would shake the system, what would be the first reaction to the system? What happens? And these excitations, they also behave in a highly unusual way. And now we're getting really, really deep into this the phenomenology of the state. But what these excitations do is that they now behave in a way that is, again, very different from any kind of particles that we know. So they're not bosonic, they're not fermionic. They don't fit into our complete framework of particles. And now we're going away from the charge, but we're actually going into quantum statistics, so on the statistics of particles, and these can't be explained by any of those statistics. And that's why they're called anyons. And some of these anyons are now so exotic that we can now pair this robustness that I mentioned earlier with the excitation behavior of these systems, and that is now something that can be used for quantum computing, or is believed to be used to be possible to build quantum computers with this. And since these excitations would be so robust, the quantum computer would be robust. And we all know that this is one of the biggest challenges right now to make these things robust, to make quantum computers robust, because they're so fragile, these quantum states. And here we have something where the quantum states are not fragile. So essentially what we, just to wrap up this path, current day application of some of these fractional quantum Hall states is to use this robustness that I mentioned earlier, and use it in a smart way such that now we can build quantum computers that are also robust, and therefore we can beat nature by saying we can build quantum states that are not fragile by exactly using this kind of effect. So it turns out that through all these precision measurements and fundamental questions, we now end up at a place where we have a completely new application for the quantum Hall, for the fractional quantum Hall effect. Very surprisingly, but very beautifully also.
So we're back now from a after a small technical defect, let's say, and what we were saying before the break was that these particles now act like neither fermions nor bosons. Would you mind elaborating a little bit on what the difference actually is? So is it in the anti-symmetry versus symmetry aspect of the wave function, or what is it actually that changes with this? And if it is the symmetry, anti-symmetry aspect of the wave function, how can you have anything different than those two? That seems to me like a binary sort of, a binary choice.
So just to be clear, we're talking about the excitations of the system, right? So it's the way these particles now start these excitations. And it turns out these excitations here are actually holes in the system. And these holes, they usually, when you take a particle out of a system, you get a hole, and that hole will be exactly as large as this particle. So in case of an electron, it will be the mass and the charge of one electron that's missing in your material. Now in the fractional quantum Hall state, these excitations are actually they're called quasi-holes because they don't have a full charge. They have, you may guess, the half charge that we already talked about earlier, or third, or it can be many different fractions. And in fact,
there are still more fractions being discovered. So you get a hole that has now a fractional charge. And so these are these excitations that we're talking about. And what happens now is that if these were fermionic or bosons, as all other particles are, and also all excitations that we know, they usually behave like particles. If I exchange two of these excitations, so if I move them around one another, so I move one of these excitations to the position of the other one, and then the first one back to where the other one was. So then my global wave function indeed, or all observables have to stay the same. And everything that we look at the wave function and so on is always the squared of that. And so it actually has to be either unchanged or the wave function can get the minus sign. So the idea is essentially that, if I exchange two particles and then I exchange them a second time, I'm back at my original at the original state, so it has to be the same. So if I don't do it twice but once, then that means it has to be half of that, and half of that can either be still the plus sign because then nothing changed, or it can be the minus sign and then I get this second minus sign with the second exchange, and so I end up at my original situation. But here it's different. So I move them around one another and still I get something that's different from a plus sign or minus sign. And that can be any complex phase. So a complex phase, essentially you have I, or you have anything else that sits on mathematically speaking on the unit circle, and if you do it once or twice or three times, you still may not end up at exactly the same state as where you started with.
So does that mean, so maybe this is a naive question, but is the state somehow path dependent then? Like you would have two states that from an outsider's perspective look the same, right? If these particles end up in the same situation, but nevertheless the wave function describing them is different. So they're path dependent in some way.
Well, if you just have two excitations, it's not path dependent because it's actually robust against this path. We have a robustness again. It doesn't matter how I go around the first particle, I just have to go around. If I don't go around, of course, then it starts to be different, right? If I go, like, see here, these two particles, and if I would go not in a circle, but like almost to the second particle and then back, then I didn't exchange them, and so that means I go back to where I started with. But if I actually go around, and no matter how I go around, but as soon as I go around, I get this phase factor, which is not plus, not minus, but can be anything in between. And since it can be anything in between, we call these particles anyons. So that's the name that people came up with, and the fractional quantum Hall system is really one of the paradigmatic systems that has these kind of anyons. There are other states, other systems that we now know of that also are predicted to show these anyons, but the fractional quantum Hall state is really one of probably the first and still the most iconic one, I would say. So yeah, that's something that's really fascinating about these systems.
Are you then introducing an additional, let's say, dimension into your state representation? Because if you have a fermionic or bosonic system, you wouldn't have to specify that phase component, right? You would kind of know it a priori. It seems like we're introducing another dimension into the representation, but maybe that's me, not thinking appropriately about this.
No, it's maybe it's actually a very nice way to think about it. It's so. They're actually, it gets actually more interesting. So there are different kind of anyons. There are different kind of fractional quantum Hall states, and some of them, what happens is that if you move them around each other, you get a different phase. So which means that again, your global state, you will not see it anymore because you always look at your wave function is always, or the observables in the end are always like the square of that. So it's in the state, but you don't really see it because it's just a phase. But there are also some anyons which really change the entire state. And in those cases, I think I agree with your idea of thinking of this as a new dimension, because it's almost like you go in another direction that you couldn't see before because your state is now different. And usually your state changes by moving something away or rotating it, right? But maybe you move it or you take particles elsewhere, but here you don't take anything elsewhere, but everything looks the same from our perspective. But it is not the same. And that's why I think your picture of this new dimension is actually a very nice one. So it's almost like there's a hidden dimension along which you can move, and you can move there by exchanging particles that for us usually we would not think about this as changing the state, but in this case it does. So I agree with your picture, at least for this latter part of the anyons, where it's more than just a phase, but it's actually changing the state.
Okay, and if we talk about that change now, like the phase change in the first example for these states, is that closely tied now to the notion of having a topological state and also the implementations or the applications, let's say, of quantum computers for this. Because my understanding of topological quantum computers is you would actually manipulate, let's say, the qubits that I take you would represent with, with one of these vortexes, for example. That the way you manipulate it is by actually physically moving that part around. So is this phase change then, closely intertwined with that notion?
So yes, well, for quantum computing, you need the latter part of these anyons. These are called non-abelian, and these are the ones that actually change the entire state and not just the phase. But then, otherwise, I fully agree with you what you said. It is about this topology, and it's exactly the topology is really closely tied to that. So you would encode your qubits in, for example, these quasi-holes that you have. You have some excitations that you pin, for example, and then you move them around one another. And again, this motion is topologically protected. So how exactly you move doesn't really matter as long as you move around the other particle. And how you now move these particles around each other, that's called braiding. So in which order and how, and in which direct orientation and so on, you would now move these particles around one another. That will, in the end, encode your quantum computation. Yeah.
Okay. Maybe we can focus a little bit on the actual implementation and sort of more the details of your particular contribution in this paper. So you're implementing this structure now with the help of ultracold atoms. Could you maybe describe what you've done differently with this kind of physical implementation compared to some of the previous ones? Because I take it that these states have been observed before, but not necessarily with the same kind of architecture that you're now laying forth in this paper.
That's correct. So in solid state systems, people have looked at this with electrons, particularly in electronic gases, 2D electronic gases, for decades. And it is usually a very high level experiment, right? So high level in the sense of you can't really look into the details of it, but you have your sample and you would look at the resistance and the conductance and these kind of observables in the solid state system. And there have been proposals how this would look locally in how exactly the wave function would look like, in particular this kind of vortex structure here that I've mentioned, but it's really difficult to actually show this in a solid state experiment. And so this was one of the motivations, and also other motivations, for example, all the nice features about this data we already talked about. These were motivations why people in the quantum simulation community said, it would be really, really nice if we could actually realize these states in a really, really nicely controlled quantum platform where we can see each particle, we can really move them around, we can do with them almost what we want. And if we could do that, then maybe we can verify these wave functions. Maybe we can also understand some of the not well understood properties of these fractional quantum Hall states, and maybe even use this for topological quantum computing. And so this was like a general motivation in the quantum simulation community and also in the cold atoms community to be able to actually realize these kind of states. And now in cold atoms, we have one big problem, if it comes to fractional quantum Hall physics, namely, what we usually do is we realize these systems and they really look like solids. We have these optical lattices, periodic landscapes, and everything looks really like electrons in a solid. We can even do this with fermions and with bosons, so in that sense we are even broader than solids because they always have fermions. Here we can also look what would happen with bosons. But there's one big problem, namely we always work with neutral atoms. So our atoms, they will never see a charge. And that's mostly fine because we can let them interact in different ways, and so it's kind of like a Coulomb interaction, although it's not from charge, but usually it's fine. So a lot of phenomena work fantastically well. But the one thing that always bugged us is that we can't do magnetic fields, because magnetic fields, they only couple to the charge. So Lorentz force is proportional to the charge, and if the charge is 0, there's no Lorentz force. And that means that if I have a magnetic field, the system can't really, my system would not see it. I can't really simulate anything that is related to a magnetic field. And quantum Hall physics, of course, is intrinsically related to strong magnetic fields. We have to put these 2D samples into strong magnetic fields, and without any magnetic field, it would not be possible to see anything. And so there have been some tricks developed over the last 10, 15 years, almost 20 years now. So people have really developed some tricks of how one could do this. And there's two different ideas. One would be to rotate the system, and the rotation turns out to be very similar and mathematically identical to a magnetic field. So you can actually kind of emulate the behavior of a magnetic field. And again, it's a very abstract level in which way we are realizing this 2D system here, but it's in the end it turns out to be the identical physics, and therefore we can also study the identical physics. Here we use the second approach that has been developed, and it is based on laser beams that essentially you have when these particles move, they get a kick from lasers. And that kick is like if you use two laser beams in the right way, you can just do it right such that the particles always get a kick whenever they would move. And that kick now is exactly in a way as the Lorentz force would be. So it's always orthogonal to the way the particle would move. And so in the end, what we do is we kind of mimic the magnetic field through this magnetic field through laser beams, and we end up at exactly the same system as electrons in a solid, except that our particles are not charged, but they behave exactly as if they were charged in magnetic field. So it's a very subtle technique, and I don't want to bore you with the technical details, but the important part is that you end up with exactly the same situation, and since we know that, we can also trust that the physics has to be the same.
Mm-hmm. One follow-up question is, how do you model the electric field? So my understanding is normally when you would observe this effect, you would have electrons propagating through some material and in a plane, and you would have an electric field that's dragging them along, let's say, and then you would have a strong magnetic field that you apply to it. Now we discussed how you would emulate the magnetic field. How would you emulate, if you even need to, the electric field and the propagation of the atoms? Do you simply make them propagate in some other way, or is there something else that you need to actually push them with, let's say?
Yeah, so the electric field is usually applied when people want to measure the transport of these systems, right? In this particular experiment now, we actually only looked at the ground state, so not even at the transport behavior, but really at the ground state. And if you have now the power to really look locally into the system, you can get all of the transport behavior even from the ground state. But we could also actually mimic this kind of electric field, because what it actually is a kind of a force on the particles along the direction of the field. So we can also do this by applying a tilt to the system, and that gives you exactly a force along the direction of this tilt, and with that you get exactly the same as for an electric field usually. Yeah. So in this case we did not introduce an electric field, but we could.
Mm-hmm. Okay, interesting. So if we move on to the next figure, maybe we can have a look at this one, which somehow represents the preparation of the system. So you did it with two atoms, is my understanding, and those are the ones that are represented, I guess, in the initial state here. Can you talk us through how the preparation from initial state here to final state actually, how do you go from the first state to the last one, and what are you trying to achieve with that?
Yes, so maybe that's actually a thing we should very quickly mention and maybe emphasize. So these are two particles. So in that sense, it's a very minimal system of a fractional quantum Hall state, right? Where you barely have this vortex motion captured. And it's the reason why we started with two particles is because it was this long-standing challenge to realize this kind of state in a quantum simulator. And it turns out that with larger particles, people have tried and they couldn't really get there. And so we thought, okay, let's first start with two, and if we can get this right, then we're going to learn how to do more particles. So it's really, you can think of this as a first step towards getting to system sizes that maybe can be useful to answer unknown questions. At this point, it's really more like seeing the state microscopically, but it's not yet at the level where you would be impressed by the size, I would say. Yeah? So we started with these two particles, and we do something that's often called adiabatic quantum state engineering. And so what that means is that if you start in a particular quantum state, and then you change it very slowly, and so slowly that you never really excite the system, then you will also end up at this ground state at the end. Right. So you change your system parameter and you never really change them very suddenly, and therefore you always stay in the same state. And that's the approach that we did here as well. So we start with a very simple state, the simplest that you can imagine, namely just two particles on two lattice sites. So we have here 16 lattice sites in this optical lattice, and particles are restricted to this confined region, so they can't hop out of this region. So they're always only 60 lattice sites, and at this point we now apply strong tilts. So actually they're kind of electric fields if you like. Yeah. So there are strong tilts along both directions, x and y, and so these two particles, they are now the ground state of the Hamiltonian. You can really think of them as like two balls, and they're in this corner, and so that would be the ground state of the system. And now we slowly remove these two gradients along the two directions until these particles have spread out through the entire system. If we do this slowly enough, then you stay in the ground state of the system.
And it's only after that then that you apply a magnetic field, or is that applied also during the course of this propagation?
The magnetic field is always applied to these lasers, but at the beginning, of course, they can't move because they are confined to their corner. But as they spread out, they experience more and more of this magnetic field, and they will always stay in the ground state.
Mm-hmm. Okay, and then I think the propagation of this is actually represented down here, right? So what you change is the potentials that are keeping these atoms in place. Is that the correct way of conceptualizing it?
Yes, exactly. So we first change the tilt along the y-axis, and that's how you can see that first these two balls, these two particles, they delocalize along this tube, and then afterwards we start to remove the gradient along the second direction, and then these particles this tube expands into the full 2D plane until we finally end at the ground state of this 4x4 system.
Mm-hmm. Okay. If we move over to the figure G here, can you describe quickly what this represents? So we have this fidelity on the y-axis, and then the flux representing the magnetic field on the x-axis, and then we have a drop in the fidelity where we transition between these two states. What is this drop in fidelity coming from, and why do we observe what we observe here?
Yeah. So this preparation procedure that is shown on the previous panel. Is what you just had here, exactly. So this was done at a particular value of the magnetic field, and it's done at a value where we expected this fractional quantum Hall state to occur. So they don't occur for all magnetic fields, but only at specific values. And you can, it's something called a filling factor at which you would expect this to happen, and so we tuned our magnetic field to exactly the position where we expected this to happen, and we thought, yes, that looks like the state, but how can we make sure that now this is actually the state? And one first thing that we wanted to do was to map out the phase transition. There must be at some point this transition from what we called earlier this normal state, where particles just in the ground state, they're just in there, versus where they're now in this fractional quantum Hall state. And this transition point is a point where this adiabatic preparation sequence should fail, because it is a point where the excited states and the ground state, they touch. And so as I said earlier, you can always stay in the ground state if you are so slow that you never excite anything. But now if excited states are not separated in energy anymore, then you will actually fail. So essentially, excitations can happen arbitrarily easily, and so that means that even if you do it very, very slowly, you will still lose your ground state. And so we thought, okay, we can essentially do a spectroscopy of the system. We can measure by measuring how easy it is to excite the system, we also measure how close the excited states are to the ground state, and we know that wherever these excited states are close to the ground state is the phase transition. And so that's exactly what you see here with this dip. So this minimum, that exactly shows where it failed, where we could not prepare adiabatically anymore, and therefore this shows us it's the transition point between the normal phase and the fractional quantum Hall state. Okay,
I see. We are very short on time, and we have a lot of figures to cover. So we can jump to the next one. I think the next one is actually, not the next one, but this one I think is quite interesting because it sort of shows this, would you mind describing the top figure here, what this represents?
Yeah.
Because I would guess this is sort of the best representation of what actually happens in these systems.
Yeah, I think it really nicely captures this vortex pattern. So, and I think it really shows you what you can see and why these quantum simulations actually can be useful, because they can visualize something that is not really possible to see in a condensed matter scenario. So what you see here is the 2-point correlation. So what you see is essentially the center of mass correlations, the relative coordinates between these two particles. And red here shows you that this occurs very often, and blue shows you that it doesn't occur very often. And there's a striking difference between the normal phase and the fractional quantum Hall state. So on the top left, right, you see that it's pretty flat, so you don't really see a strong difference between the distances. But on the right panel, you can see that in the center point, so when two particles would be on the same lattice side, that essentially never happens. And then as the farther you go away, the more likely it is that this actually happens. And this red box here shows you that the farther the particles are away, the higher is the chance that they actually see each other. So there's a good distance at which particles like to be from each other, and that's exactly the size of this vortex. So that really shows you here, yes, these particles move around in each other's vortex, and that's Robert Laughlin proposed this in the 80s, and it has always been assumed that this is what happens, that it makes very much sense that this is a wave function. There's not really a debate about whether this wave function is correct or not, but nobody could ever see it and verify it. And here you can really see that this wave function looks exactly like Robert Laughlin at the time proposed it. So I find it very beautiful that you can actually see this in an experiment, that yes, Robert Laughlin was right.
Yeah, it's very cool, and such a long time afterwards as well. Like you have this massive gap between the theoretical prediction and then you actually get the validation for it. In terms of affecting this vortex and the size associated with it, is there anything you can do to manipulate that?
The size is pretty much given by the density of the system and the magnetic field strength. So in that sense, you could change it by changing the magnetic field strength or the particle number, and that would make it either smaller or larger. And that's definitely possible. You would probably want to make the system a little bit larger, because on the 4x4 system, if you start to make your vortex even larger, it will kind of hit the walls. But that's definitely possible, yeah. And that's actually something we would like to do in the future, to extend the system size and therefore have a bit larger vortices, have a bit more ways to manipulate in the system than right now, where this box is kind of the minimal size at which you can still see physics, yeah.
Okay, great. We need to start bringing it to a close, but if there are any more properties, like regarding the things that you found in the paper, because we have quite a few figures, any property of these states that you think are particularly noticeable and that you would like to show, like as a last figure perhaps, or just make a remark about?
Yeah, maybe if you want to move on by one more figure, the next figure. So this is just another very nice example of where you can bring these quantum simulations together with condensed matter physics. So in condensed matter physics, we talked about this fractional plateau of a fractional charge. So that means there's a conductivity that would correspond to half an electron moving, so half fractional charges. And in this case, we did the same, but without actually exciting the system. And there's a relation between the ground state, the ground state density distribution, and this conductivity. And I think that's a relation that's very nice to see here, because we can actually map out the individual densities on each different lattice site, because we can measure that locally. And what we do now is we manipulate the magnetic field a little bit. So we do essentially what you said earlier with this vortex. We change it, but just a little bit. And that now changes the density in the bulk. So the bulk in this case are the central four sites. And this change in density now encodes the fractional Hall conductivity. So we can directly verify that these particles indeed move like half, or behave like half electrons, like half particles. Yeah, and that's encoded in the change of the bulk density in the system. So the bulk density increases a little bit with the magnetic field, and this change is exactly proportional to the Hall conductivity, and that's something we can see here by just verifying that this change actually matches this Hall conductivity. So indeed, we can measure the fractional charge of these particles here, and in this case, it's 1/2. So for electrons, it's usually odd, and for bosons, it's even. And in this case, since we have bosons, it's odd.
Mm-hmm. Okay, awesome.
Excuse me. Since it's bosons, it's even. Yeah. Yeah.
Okay. In terms of next steps, so that's also something I want to know just before we close. Given the research that you now made, the results that you got, are there any follow-up actions that you would like to see, either from the wider research community, or that you would like to, let's say, engage in yourself, maybe with the research that you're already doing, or something that you would like to do going forward to sort of further the insights that you got from this paper?
Yeah, so I mentioned one direction we definitely need to get a little larger, and we have plans and actually preliminary results that it should be actually fairly possible within what you can do to extend this. And now we're not talking like 4x4 sites anymore, but 10x10 or 12x12 system sizes. And there you can really see interesting things that's beyond of anything what we can compute. So that will be really exciting to go there with more particles. And there we can now really look at these excitations, these elusive excitations that we mentioned earlier, these anyons, and with optical potentials you can trap them essentially and move them, and all these beautiful things that we talked about earlier, like these quasi-holes, seeing these quasi-holes and moving them and understanding what happens when you encircle each other with these holes. These are the kind of things we want to look into. And as I mentioned, some of these states are really so exotic that you can do robust quantum computing with it. And so I think that would be definitely a long-term goal towards we want to work. But right now it's more on the fundamental level. Can we understand these excitations better? Can we isolate them? Can we move them around? Can we merge them? I think these are the next questions that we want to, or the next experiments that we want to perform with this.
Mm-hmm. Wonderful. So then let's close it there. Julian, thank you very much for taking the time. I really appreciate you talking to me.
Yeah, thank you for having me. It was really, really interesting.